in a cyclic graph directory structure, okay, a file can have 2 or more different names, okay, for the reason of sharing or better organization or whatever. Okay, if we try to delete, for example, the file /dict /w/list, okay, then the file /dict/o may be lost. Because these two are point to the refer to the same file. Okay. To resolve this possible problem, the possible solution is we assign each file an integer which counted the number of references to that particular file. Okay, so we call it a reference count. Okay, and this kind of a mechanism sometimes we call it hard link. Okay, so each name to the particular file counted as a hard link. Okay, because the two hard links, the semantic meaning are identical. Then there's no primary name or secondary name or whatever. All these different names, they are equally important. Okay. Or another way is that instead of using the hard link or tree, all the names are equally important. Another mechanism is we create a new special file in the directory entries. Okay, we call it soft links. Okay, that means instead of we distinguish those names, the first name associated to a particular file is a primary name which kept there. Okay, and the other names to an existing file. Okay, we create a special file for that. Okay, we are not let this name directly associate to the existing file. Instead, create a special file, and the content of that special file is the page name, the real page name of the original file. Okay, that means a hard link is a primary or real page name of a file. A soft link is just a indirect mechanism. Okay, inside this indirect file or special file, a soft link file, we recall the real page name. Okay, so in this way we don't need to maintain a reference count because the real name for each file there's only one name, but these other names we maybe call soft link names. They are not directly mapped to the original file. Okay, we go through these indirect spatial files. Okay, so however, when we open a file which contains which is a soft link spatial file, then we will not open the file directly. Instead, we resolve the link, follow the real page name, and to locate the real files. Okay, and if this real page name is not exist, then this soft link become embedded. Okay, so by distinguish the names, okay, one is the hard link names, okay, and the others are soft links. So once we delete the hard link, then the file will be deleted. Okay, and so if the system only use hard link, then we need to have a reference count. Okay, but on delete these hard link entries, the reference count will be decreased by 1, okay, until the reference count becomes 0. Then the file will be removed from the file system, okay. So by to resolve this acyclic graph, okay, a file may have different names. Either tree or the names are the similar important, okay, with hard links, or we create a primary name for the file, and the other names are secondary, so that they all use sublinks, okay, and then but by using hard link mechanism, we need to have a reference count. If we only use sublink, okay, we only allow a file to have a hard link, and the other names are all sublink. Then we don't need to have the reference count. Okay. The last directory structure is general graph directory. That means you can create as many names as possible without any restriction. Say a cycle, and a cycle may exist. Okay. However, if we use reference count and hard links, then cycle may cause this reference count become embedded, become okay, improper. Okay. For example, okay, let's see this particular example. Here we have a directory file, okay, which contain 4 entries. This file, the physical file, is maybe called underlined file A, okay. They have 4 entries: text, mail, and count, book, okay, /AVI, okay. And also we have another directory which is /AVI /book, okay. And this one has 2 names, okay. One is /AVI /book, another one is /GIM /book, okay. So they all point to the same file, okay. Okay. For example, okay, well, if the /GIM /book is the first name, and then we create /AVI /book, that's the another name for this /gym /book. And then the reference count of the file B, okay, or this directory will become 2, okay. And when we under this /AVI /book or /gym /book /AVI, we create this entry and let it be the file of directory A, okay, /AVI. Then the reference count of directory A will also become 2, okay. So you see, then there's a cycle exists here, okay, /AVI /AVI book /AVI /book, okay. So we have cycle here, okay. Okay, here we have this the cycle here, okay. So after we create this cycle, if now we try to delete /gym /book, okay, we try to delete this entry, okay. So the reference count will come 1, okay, and then we delete /AVI /book, okay. So this directory B, the reference count will become 0 now. Then and this whole directory will be deleted, okay. However, the deletion of this one will not change the reference count of A, okay. The reference count of A is still 2, okay. And then we delete this /AVI. So the reference count for A become 1, okay. But after this one, this link was deleted, and this was deleted, this file was deleted. This directory A will not be deleted, but there's no other reference can point to that one. So, okay, after we delete this one, the actual reference to directory A should be 1, but the reference count is A. So this directory will never be removed from the system, even we delete this /ABI. And we delete this entry, this file, because only the reference count become 1, but this part is still there. Okay, we need other mechanism to eventually find out that this directory is floating. It cannot be referenced by any name after this. Okay, so you can see if there's a cycle, then it's possible create even if we only use reference count, that it's possible create this kind of situation. Okay, so to avoid the problem generated by a cycle, either we restrict, and we can see that the problem for this cycle is that we allow the hard link to point to directory. Okay, we create directory, file name for create a directory with multiple names. Okay, so if we did not allow a hard link to point to directory, only to files, okay, then it's possible, okay, all this cycle will not involve with the directory. Then it's possible. Then there's no problem for this. Okay, the problem will cause this floating directory usually is if for the file the cycle involve only files. And there's no hope. The reference count is still valid. Okay. Or another way is that, okay, we periodically the system will using garbage collection mechanism to detect that, okay, this directory is useless because no one is reference to that, so, and declare the resource associated with this part. Okay. Okay. Or to avoid create cycle is that when we create a new hard link, we check the cycle existence. Okay. The last approach is that instead of using hard link, we only use soft link. Okay. The file can only allow to have a hard link, but can have multiple soft links. Okay. So the file can have only one real name. The other names are indirect. The sublinks are indirect names. Okay, so there's no problem. The indirect names become invalid. If the hard link was deleted, then the sublinks become invalid. Okay, but the problem, the garbage. Okay, this is leftover directory or files. They will never have this situation happens. Okay, so to deal with the problem caused by the general graph directory mechanism, actually is a cycle involved with the directory. We can resolve that by using these 4 approaches. Okay. Now we have the understanding about the directory structure, the file systems, user label directory structure, not device label directory. Okay, let's see how a file system actually can be implemented on top of a disk. Okay, a file system usually was implemented or resides on a secondary storage or maybe disks. Okay, and by using this, we can the system can provide easy and efficient access to disk by allow data or persistent data to be stored, located, and retrieved much efficient and easy without application to knowing the detail about how the disk works. Okay, and so on. Okay, and in general, because remember, a physical device usually has a device directory contain a number of entries associated with the file, the physical files. Okay, so associated with this, okay, a file should have metadata to describe information about the particular files. Okay, and this metadata sometimes we call it file control blocks. It's like a process. Okay, every process you have a process control block to specify the attributes associated with that particular process. A file is also okay. We need to have some management attributes. So the file system can properly manage and give better resource utilization or performance. Okay, so this file control block is used to store the meta information about a particular file. Okay, and in general, this device directory, okay, or the physical disk device is used to maintain these file control blocks of all the subdirectories and files, the attributes of this directory and files. Okay, they are maintained. So in general, each file control block is associated with a device directory entry. Okay, a typical file control block will store, maintain this information about permissions of file and the data, the dates, okay, or times, okay, the time of date creation and last access and last update information. Okay, and also some ownership information. Okay, and the current size of these files. Okay, in general, okay, maybe in bytes or in blocks. Okay, and the data blocks, the address of the data box or the number of data blocks used. Okay, and pointer or the direct address of these data blocks. Okay, or indirect address of these data blocks. Okay, later we will discuss this. And this information also they will associate with device directory. So each device directory entry may associate with one or file control blocks in general. Okay. So when operating system initialize a file system, okay, underlying the system may have attached with multiple file system and some. Okay, but anyway, for each attached file system, okay, operating system to avoid to be able to efficiently retrieve or store information from this file system. In general, we need to maintain some data structure in memory so we can get the fast response or fast access to the file. Okay, so in general, okay, there's a spatial data structure in the memory. They maintain the file control block of the files. Okay, and those caged file control block, okay, usually associated with file which is currently being used. Okay, that's why most file system they support this open interfaces. So before an application can use or access a file, they need to first tell the operating I would like to use by this open API. Okay, so most systems they use something like this. You give the file name or path name of this file, okay? And the operating system, the file system will try to find out this file, okay, from the file system, and then catch this file, the file control block of this particular file into a directory, a spatial data structure in memory, okay? So subsequently, after this open to access this particular file, they don't need to go to the file system to search for the information about the file. So the file control block is already being cached. So the purpose for open is to cache this meta information of the particular file in the memory. Okay, and the file may be a file or a directory. Okay, so the entry cached in here will be the FCB associated with the actual file or associated with a subdirectory. There's either way. Okay, but they don't. Okay. So after we issue the open, then we can use a GUI drive to access this particular file. Okay. In general, most of the operating system, model operation, they will maintain we call it per process open file table. Also, there's a system-wide open file table. This system open file table is associated with this directory structure. Okay. In here we say okay. Okay, so after we open the file, okay, and the file control block will be moved into here. And this file control block, inside this file control, they have some information about data blocks, the address of the data blocks. Okay, so and because a user process may open several files simultaneously, so each process they associate an open file table. And this table, they will store a pointer, point to this open file table, okay, system-wide, okay, the whole thing. And they may have two user process. They open the same file, so they both have its own per process open file table, and with index or pointer point to this same system-wide open file tables. Okay, so by using this two layer of these open file tables, one for per process, one is system-wide, then it's possible we can easily handle multiple simultaneous usage of the same file by different user processes. Okay. And so this system-wide open file table, for example, the basic file control block information are stored in here. However, the per process open file table may store is process related per process related information. For example, the access mode. Okay, because this open for process A may open for read, but process B may open for write, for example. Okay, and the file position or may be different. Okay, a process may already go through several access, so the position will be in N, and another process may just in different position, current position, maybe in position M. Okay, so this kind of per process related information will be stored in this per process open file table for different process. Every process will have its own per process open file table. Okay, to maintain those unique the open file, but unique to that particular process. Okay. System-wide, because for the data block address and other file control block attributes, they can be stored in the single system-wide open file table. Okay, so by using this kind of in-memory data structures, the organization can manage the access, can make the access to file system become much efficient. Okay. Another mechanism used in modern operating systems is that virtual file systems. Okay, we have mentioned a little bit before. Okay, usually an operating system or any system may support multiple physical file systems. For example, this is a particular example. The file system may have extension 4, Unix or Linux extension 4, and FAT32. That's the DOS mechanism, or ISO 9660. Okay, special standardized file system. Okay, but they are associated to they may associate with different block devices. Okay, by using different file system. Okay, to implement it. But to make application programming easy, in general, we will support a single abstraction with same APIs. This we call it virtual file systems. Okay, so through this virtual file system, okay, the user application, they use the same system call to access the actual file system, but through this virtual file system, they map this interface to different physical file systems and so on. Okay, so the API supported by VFS is much is standardized. Okay, so the application programmer did not need to learn this API for this specific file system. Okay. Now we have mentioned that the directory has structure, file systems direct structure, maybe single label directory, maybe two label directory, or tree hierarchy, or a cyclic graph, or general graph. Okay, but what's the most common mechanism for this directory? Okay, a directory is just a special file. Okay, it contains information about underlying subdirectory or files, namely mapping mechanism. Okay, so usually a directory contains a lot of entries, and each entry will have at least this name and reference pairs. Name is the file name, and reference is just referred to a particular physical file. Okay, and the name is used to map to a physical underlying file. Okay, that's mapping to the metadata, or the file control block, and real stored or maintained persistent data. Okay, or sometimes some system they prefer use name and metadata together as the key to map to the physical data block. Okay, and these two kind of approach, you can see that the Unix use this first approach, that the name itself can be used to retrieve its metadata associated and data blocks and real data. Okay, but in this FAT file system or DOS file system, they use this name and the metadata together. They can find out the data blocks. Okay, let's see later how this difference. Okay, so this entry, okay, this entry, the directory entry, okay, can be organized either as a linear list, okay, or a hash table, okay, to search, because we need to, in general, we use name to search, okay, to search this reference, to find out this reference, and use reference to retrieve data, okay. In a linear list approach, we need to search a large directory because it's a linear list, so we can only use sequential search, okay. So if the directory has a lot of entries, then the efficiency will be low, okay. So the better way is to catch this frequently used entry, okay, and this system-wide open file table is serve this purpose. Okay, it's a cache for frequently used, because if anyone opened, then any process open the file, then you cache its related information in memory. So the next time the other process will try to open the same file, they will search in here instead of go to the disk to find out this information. Okay, if it exists in here, then the search is much. Okay, it's like this. Okay, it serves the purpose of the cache. Okay. Another way is that we can associate this DNS with a hash table. Okay, so the directory search time can be decreased. Okay, then we will anticipate all the problem associated with the hash table. Okay, the collision and the size of the hash table need to be considered. Okay. Either we can use a more complex data structure to maintain the directory entries. Okay, for example, maybe use B-tree or H-tree to give a better or more efficient searches. Okay, and this in general is a balanced tree. So the performance for the search will be limited to the depths of the trees. Okay, this is the organization for the directory. Okay, and for data blocks, in the disk, okay, we need to manage how these disk blocks be allocated and deallocated, and to manage. Okay, in general, there are several mechanisms can be used to manage these disk blocks. Okay, some particular frequently used mechanism are contiguous allocation mechanism, or linked allocation mechanism, or indexed allocation mechanism. These are three typical mechanism. Okay, contiguous allocation means that a file is assigned to a set of contiguous blocks on the disk. So when we create a file, require n disk block, then we try to find n contiguous free blocks on the disk. Okay, so a simple, easy mechanism can be used. Okay, to maintain this information. So for each file, the associated disk block information will be the starting location, the block number of the starting, and the length, how many blocks are used. Okay, so 2 parameter or 2 disk address will be enough for this contiguous allocation. Okay, and the advantage for this is that it provides a very fast random access to any file, to the file, any blocks of the file. Okay, because these blocks are contiguous. So you from the starting location, you just plus the offset, then you can directly calculate the block address of any position in the file. Okay, and the problem is that for this kind of allocation, the files may not be able to grow easily, because if a file already occupy n blocks, and there's no rules to extend this fire because the boundary the next blocks already been used by other fires. Okay, then we will need to allocate the n+1 blocks. The file system would require to find out 3 blocks of n+1 in the disk. Okay, other place, and then move the whole file to there. Okay. That's one way. Okay. Another way is that we if a file require n blocks and to avoid this dynamic moving around of the files. Okay. Then we may allocate more or then require, for example, you require n blocks, then we allocate n plus k blocks, contiguous blocks for the particular file, and then so the file can grow until n+k. And so to reduce the data movements in the future. Okay, but however, if this k well, then the initially those k blocks will be wasted because it cannot be used by other files. And if the file eventually grows to n+k, then it's all right. But if the file never reach this n+k blocks, then you have some disk blocks, they are wasted. Okay, and this kind of it's like a memory, okay, waste. So this we call it's an internal fragmentation problem. Okay, you have some storage is pre-assigned to a file to R, but never get used. Okay, so a compromise of this contiguous allocation is we sometimes some file system that they use extends. Okay, instead of contiguous for the whole file, so they allocate a contiguous chunk of blocks. Okay, called extents at a time. Okay, and this can do the extent, the size of extent may be fixed, so they can keep track of all extents information. Okay, so initially a file can only have one extent, and if the whole extent is full, then allocate another extent, and this extents they don't need to be in the contiguous location of the disk block, the disk area. They can be registered in 2 different chunks. Okay, so to avoid this, to reduce, not avoid, but to reduce the problem of this growing waste. Okay, so we limit the waste to the size of extent. Okay, because after you allocate an extent, the file may not be grows to the whole extent, but in average, the waste will be half extent. Okay, if the distribution is uniform. Okay, so only the last extent may have some space wasted. So the size of extent, that means will be the design choice. Okay, and so on. And the second approach is we call it linked allocation approach. You link all the data blocks of a file into a linked list of blocks. Okay. So directory entry contain a pointer to the first block of the file. Okay, and each block contain a pointer to the next block. In here, the pointer is the disk address. Okay. So the problem is that the random access become difficult because you need to go through the first block, second, and then to find out the nth blocks. Okay, and another problem is that each disk block they were not used. Or for example, if a block size is 1K, then we need to have if disk block address is occupied 4 bytes. Then each block you cannot use the whole 1K 1024A, 1024A, okay, will be 1K minus 4 bytes. Okay, it's not 1K bytes. Okay, so that generates some difficulty because when you try to compute a particular position n in a file, now we are not, instead of n divided by 2 of some powers, for example, 1K is 2 to the power 10. Okay, the division is much easier in the binary. Okay, but if we make a division of n divided by 2 to the power 10 minus 4, okay, then it's much difficult to implement this kind of division. Okay, because it's not a binary division. Okay, so this has a compromise of this linked allocation will be use a file allocation table or fact table. Okay, that's the mechanism used. It still is a link, but instead of put a link in each data block, we merge all the links into a special table. We call it file allocation table. Okay, so each data block as a whole, they can all used to store data. A block size is still 2 to the power some k. Okay, and this link or pointers or disk address, they are all collectively together in a table. Okay, we will see in the next slides how this file allocation table works. Okay, and the last approach is indexed allocation. We store all this block address pointer of a file on intermediate blocks. Okay, and this block we call it index blocks. In Unix or Unix-like file system, they use this name we call it inode, index node. Okay, it's a block. Okay, the file allocation table means we merge all these links. Okay, in a particular table. This table only contains the link to the next. Okay, so the directory entry for a particular name, file name, for example, test and other attributes, and the start block is in this block number 217. So in this table depends on the file system. If the file system can contain the block number, okay, the number of disk blocks, okay, is m. Okay, for example, okay, then we have a table of size m. Starting from the 0 to m minus 1 or whatever. Okay, m minus 1. Okay, and this start location, the block number of this particular file, and then the index 217 in this table will store the next block, the address of next block. So so the index 618 will still store the next blocks. The disk address is in 339. So instead of store this next block's address inside the data block, they will put it together in a table. Okay, so and this table can be cached in memory when initialize this file system. Okay, so the whole file allocation table will be copied into the memory. So this search are all done in memory. Okay, and the disk entry only contain the starting block. Okay, to access sequentially access this file, but to find out the data address, the block address will become very efficient because the search in this memory table much efficient than search in disk. Okay. So it's a variation of link allocation used in DOS and early Windows system. Okay, each disk baud contains a fact table. Okay, here the baud is a partition, another name for the partition. Okay, so it represents a file system. Okay, and have one entry for each disk blocks. The fate is shared by all files, okay, because every device or logical device, volume or partition, okay, stored together, okay. And also, once this partition or volume was allocate or initialize, this fate table will be moved into the memory. Okay, so they will contain the disk address or the next block. Okay, so the direct entry of the file only contain the first block. Okay, so you can see that the later this Windows the disadvantage of this is that the number of disk blocks, because the block become much, the disk become the size of the disk is increased dramatically. Okay, so the number of disk blocks become huge. That's why this table become out of control. The size of this table become huge. So later this FAT 30, they only used TS FAT 32. That means the 32 bits. Okay, 32 bit. The table size is 2 to the power 32 entry. Okay, it's very huge. Okay, you have a partition which 2 to the power of 32 disk blocks. It's already huge, but it's not huge enough for the modern disk yet. So later this mechanism was dropped by using other mechanism. Okay, because the limitation of this FAT mechanism is the number of disk blocks. Okay, when it become too huge, then this table become too huge to be maintained, holding the whole in the memory, because the performance of this file system depends on this FAT table. Okay, if the table must be in memory, so you can get the fast search time. If the table is not in the memory, then the performance will be dramatically affected. Okay. That approach, you index allocation means instead of store the link, we put all the disk address in the index node. Okay, so direct entry contain file name and inode number or index. Okay, index blocks the number. Okay, and each inode contain file metadata, length, timestamp, and whatever. Okay, and other metadata attributes of and also a block map. Okay, block map means for example like this. Okay, upon open the file, the whole inode will read. Okay, and get the index map. Okay. Okay. For example, the direct entry will contain the file name and inode number. Okay, and each inode may be occupied in the disk block, either in the contiguous. For example, this 99 block 99, so relative of say in some starting position. Okay, and so on. Okay, and inside this inode 99 will have metadata of this file and this disk address. Okay, say the first block or first disk block will be in here, first block, and 03 point to the second file block, and 12 point to the third block, and these are free block management. Okay, so a disk will facility maintain a free block table. Okay, so or whatever. Okay,